Hello friends, this video on P block elements part 7 is brought to you by examfear.com. No more fear from exam. Let's talk about the trends in the oxidizing and reducing agent property. So what are oxidizing agents? Oxidizing agents are one which can oxidize someone else, right? Or they can reduce on their own. And reducing agent are one which can reduce other or get oxidized. So one that get himself or herself, we can say, if we are talking about the elements in the terms of human beings, if they can get itself reduced, that means they are oxidizing agent, and if element can get itself oxidized, then they are reducing agent. This concept is clear. So in this P block, we have elements which act as both oxidizing and reducing agent. So oxidizing agents are one. Or let's talk about reducing agent first. Reducing agents are one which can itself get oxidized, right? Example, aluminum, if you see, will love to become Al+3 because it's more stable. Correct? So if you see, these guys are my oxidizing agents. Sorry, reducing agents. Why? Because they want itself to get oxidized. For example, aluminum want to get oxidized, so I'll just write here oxidizing agent first here. Reducing agent are the one who want to get oxidized himself. That is, for example, aluminum is one, tin is one, lead is one. So all these are my oxidizing agents. Let's talk about reducing agent. For example, chlorine wants to become Cl-. So from zero oxidation state, it wants to become Cl- because it's more stable, right? So chlorine is one which want to get reduced on its own, so they are oxidizing agents, right? Let me write oxidizing agent somewhere here. So chlorine is oxidizing agent, my fluorine is oxidizing agent, etc. And why is this? Because if you see, these are all chlorine, fluorine, all these halogens, they have a hungerness to get one electron. They have hungerness to get electron. If they get one electron, they'll become very stable, right? So they'll always want to become Cl-. Aluminum, they have choice of either giving three electrons or taking 5 electrons. Nobody will give 5 electrons, so aluminum will give 3 electrons. So aluminum will have tendency to become Al+3. Chlorine will have tendency to get Cl-. Oxygen also, if you see, it has tendency to become O2- actually. Why? Because if it gets 2 electrons, it will become stable. So these ones which has tendency to gain electron, that is tendency to get reduced on its own, right? They are my oxidizing agents. Why? Because they themselves get reduced and oxidize someone else. And those elements which have tendency to get oxidized on its own, right? So they are reducing agent. So we have both oxidizing and reducing agent in the P block element. So I hope you understand why they are oxidizing agent, why they are reducing agent, and why we have both oxidizing agent and reducing agent in the P block element, because we have both metals and non-metals. So typically metals are my reducing agent because metals have tendency to oxidize. For example, sodium has tendency to become Na+, calcium has tendency to become calcium+, aluminum has tendency to become Al+3. So these all metals have tendency to become oxidized and they are reducing agents. Non-metals have tendency to to reduce itself and they are oxidizing agents. So since we have metals and non-metals both in this group in the block, so we have elements with oxidizing and reducing agent both in this particular block. Let's talk about the oxidation states now. The first thing is that it has both a positive and negative oxidation states. So if you see this, for example, aluminum, if you see, since we have both metals and non-metals, that's why we have both positive and negative oxidation states. So typically metals have positive oxidation state. For example, aluminum will have Al3+. And negative oxidation state, chlorine, if you see, has negative oxidation state, right? So we have both positive and negative oxidation state since we have both metals and non-metal. And we'll talk about inert pair effect. So before we discuss, let me give you a brief introduction of inert pair effect. So if you see this group 13, the maximum oxidation state is 3. Group 14, the maximum oxidation state is 4. Group 15, the maximum is 5. Group 16, the maximum is 6. Group 17, the maximum is 7. And the group 18, the maximum is 8. Correct? This is the maximum. Apart from this, they exhibit oxidation state that is max minus 2. And why 2? Because s orbitals has 2 electrons. Correct? And sometimes these s electrons they don't take part in the reaction, so these 2 electrons are ignored, so they exhibit oxidation state of max minus 2. For example, 3 minus 2 is 1, 4 minus 2 is 2, 5 minus 2 is 3, 6 minus 2 is 4, 7 minus 2 is 5, 8 minus 2 is 6. And this effect is called inert pair effect. We'll discuss more about this in the next slide. Just understand that first thing is the p block element exhibit a lot of oxidation states. The group 13, 3 oxidation state. Why 3? For example, if you see the group 13 elements, aluminium has 3 extra electrons. So aluminium is mean enough to give 3 electrons to become stable. So it will exhibit 3 oxidation states. Similarly, if you see the next one is the carbon. Carbon has 4 extra electrons. So either it can take 4 electrons or we can give 4 electrons. So it will have plus 4 oxidation state if it gives 4 electron and minus 4 oxidation state if it takes 4 electron. So if you see carbon has plus 4 if it gives electron and minus 4 if it takes electron. And plus 2 why? Because the inert pair effect, which we'll discuss more in the next slide, where we see that s orbitals don't take part in the reaction. Similarly for nitrogen also, if you see nitrogen, the outermost shell has 5 electrons. So it has option to give 5 electrons, which hardly it gives all 5 electrons, or 3 based on the inert pair effect, or plus 2 and minus 2 also it exhibits. Similarly, fluorine also, if you see, it has plus 7 extra electrons, so it can give 7 electrons, which it hardly gives. So 7 is the one. Due to inert pair effect, it can also give 5, so it has 5 oxidation state. Since even if it takes 1 electron, it will be stable, so it has minus 1 also. But it also exhibits plus 3 and plus 1. Similarly for helium, if you see 8, 6, 4 and 2 are the oxidation states. These are all experimental values that has been found that it exists in all these oxidation states. You just have to understand that group 13, 3, group 14, 4, this is 10 minus. You can see that group minus 10 is the maximum oxidation state a group exhibit. So group 13 maximum is 3, group 14, 14 minus 10, 4, group 15, 15 minus 5, 5, 16 minus 10, 6 and so on. So let's talk about the inert pair effect which I discussed just now. So as I told, the maximum oxidation number can be group number minus 10 for all this 13, 14, 15 or p block. Right? This is the max oxidation number. Correct? That is what it says. That is nothing but the number of valence electron. Correct? But if you see, as I told, that oxidation number that is 2 units less than the maximum number is also seen for heavier elements. Please note, for heavier elements. Because as we go down the group, the tendency to form, for example, in this case is 5, the maximum is 3 actually, this also 3 and this also exhibits plus 1, this also exhibits plus 1 more often. We will discuss why. The moment you go down, it increases. Why? Because of the s orbital. The moment you go down, and this effect is called inert pair effect, as I told, right? This effect that it shows a oxidation number of maximum minus 2 is called inert pair effect. And this happens because of s orbitals and increase in size. The moment, increase in charge. Increase in charge. So increase in charge, the s orbitals are tightly held by the nucleus. If we go down from here to here, increase in charge happens. Right? Because of this, the s orbitals are more tightly held and they don't take part in the reaction. If you see, non-participation of s orbitals. And why? The moment you go down, the nuclear charge increase. Right? Since the nuclear charge increase, the s orbitals are tightly held by the nucleus and they don't take part in the reaction, and thus it exhibits only plus 1 oxidation state for group 13. For group 14 it is plus 2. For 15 it is plus 3. Like that it goes on. Hope you understand. See, these the top few elements exhibits the group max oxidation number, but if you go down, the max oxidation number that is expected to expected to exhibit, they don't exhibit, they exhibit that number minus 2 oxidation state. For example, this these exhibit plus 1, these exhibits plus 2, that is 4 minus 2, these exhibits this is 6 minus 2 plus 4 oxidation state more often, and they are more stable in the plus 4 oxidation state. We will discuss more about these when we talk about the boron and carbon family. Just understand this is called inert pair effect, where instead of showing the maximum oxidation state, it shows maximum minus 2 oxidation state, and that is why, because the moment you go down, the moment the element becomes heavier, the charge increase, and the s orbitals, they don't take part in the the reactions, and thus s has 2 electrons, so it is minus 2 is the maximum oxidation state. Let's talk about the diagonal relationship. We have talked about this in the S block elements. If you want to understand more deep into diagonal element relationship, just watch my previous videos, chapter videos on diagonal relationship. Here we see that lithium, instead of behaving with sodium, they behave more with magnesium. Similarly, barium, instead of behaving with magnesium, they behave more with aluminum. We have discussed this in the last few chapters. Similarly, boron, instead of having more similarity with aluminum, it has more similarity with silicon, and that is because of the small size of the second period element, right? So let's discuss the similarity between the boron and silicon. The first is both are non-metals. The second is both have high melting and boiling point and also high density. Both forms only covalent bond. We'll discuss this more in the next few slides. Both exist as crystalline and amorphous state. We'll discuss more about this also. We'll talk about the boron and silicon states. Both have almost similar electronegativity. The value is almost same. The hydrides of both are gaseous and inflammable. The carbides of both boron and silicon are very hard, very hard, and they are used as abrasive. They're very hard. The halides of both the boron and silicon, they hydrolyze very vigorously. The oxides of both boron and silicon are acidic, obviously because both are non-metals, so the oxides are acidic. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.